Today we will be taking the chapter Geometric Progression. What is a geometric progression? A successive progression in which the ratio between the term and its preceding term is constant and is independent of the position of the term. No matter whatever the position of the term, if we take the ratio of the term and its preceding term, if it is a constant all throughout the series, then we term the progression as a geometric progression. Let's see for an example. 1, 2, 4, 8, 16 is a geometric progression. How? If we take the ratio of the second term to the first term, that is 2 upon 1 is equal to 2. If we take the ratio of the third term to the second term, 4 upon 2 is equal to 2. The ratio of the fourth term to the third term, 8 upon 4 is equal to 2. 16 upon 8 is equal to 2. So the ratio between the term and its preceding term is always constant. Find the conditions such that x1, x2, x3, x4 are in GP. The condition will be the ratio of the term to its preceding term should always be a constant. So the ratio x2 upon x1 should be equal to x3 upon x2 is equal to x4 upon x3. This is the condition such that x1, x2, x3, x4 should be in GP. If we generalize the geometric progression, take the first term as A, the common ratio as R. The common ratio is the ratio between the term and its preceding term. Number of terms is n. Then our progression becomes A, AR, AR square, AR cube up to AR raised to n minus 1. The nth term of our GP will be AR raised to n minus 1. The last term of the GP having n terms will be equal to the nth term, that is AR raised to n minus 1. Let's see an example. The fifth term of a GP is 81 and the second term is 24. Find the digit of the GP. If the fifth term of the GP is 81, that means T5 is equal to AR raised to n minus 1. 5 minus 1 is equal to AR raised to 4 is equal to 81. T2, the second term is equal to AR raised to 2 minus 1 is equal to AR raised to 1. That is AR is equal to 24. If we take the ratio of A raised to 4 upon AR, we'll get R cube is equal to 27 upon 8. That means R is equal to 3 upon 2. The value of A can be obtained from this equation. A will be equal to 16. So our GP is 16, 24, 36, 54 and so on. Now we have to find the sum of n terms of a GP. We have a GP whose first term is A and the common ratio is R and the number of terms is n. So the nth term is AR raised to n minus 1. We denote the sum to n terms by Sn. Sn is equal to A plus AR square. So if we take this equation as the first equation. Now multiplying the first equation, multiply the first equation by R. We get R into Sn is equal to AR plus AR square plus AR cube up to AR raised to n minus 1 plus AR raised to n. If we take the difference between the first equation and the second equation, if we subtract the second equation from the first equation, we'll get Sn into 1 minus R is equal to AR term will cancel, AR square, all these terms will cancel. We'll get AR minus AR raised to n. A minus A raised to AR raised to n. Hence we'll get the formula for sum for n terms is equal to A into 1 minus R raised to n upon 1 minus R. The sum to n terms of a GP is equal to A into 1 minus R raised to n upon 1 minus R. If the value of R, if the magnitude of R is less than 1, then the sum to the n terms is A into 1 minus R raised to n upon 1 minus R, where R is the common ratio and A is the first term. If the value of R is greater than 1, then the sum to n terms become A into R raised to n minus 1 upon R minus 1, where A is the first term and R is the common ratio. What happens if the value of R is equal to 1? If R is equal to 1, we can't put this value in either of these equations, because in that case the denominator will become 0 and the equation becomes undefined. But if R is equal to 1, That means our first term is A, our second term T2 is equal to AR, that will become A. The third term T3, that is AR square, will again become A. This means that all of our terms are equal to A, and in this situation our sum will become A plus A plus A plus up till A for n times, that is equal to n into A. Our sum will become n into A. If R is equal to 1, then all the terms are equal in the geometric progression and the sum becomes equal to n times the first term. What will be the value of sum if modulus of R is less than 1 and n becomes very large? We know that the formula for the sum is equal to A into 1 minus R is to n upon 1 minus R for modulus R less than 1. If the value of n becomes very large, that means n tends to infinity. If n tends to infinity and the value of R is less than 1, that means the value of anything less than 1 raised to infinity tends to 0, and our sum will become A upon 1 minus R. This is a limiting value, it won't reach this value, but it will try to reach this value. The sum will become equal to the first term upon 1 minus common ratio. Sn sum to the infinite terms will become A upon 1 minus R. Find the least value of n for which this equation holds true. 1 plus 3. This is a GP with the first term is equal to 1 and the common ratio is 3. So the sum of n terms is equal to Sn is equal to A into R is to n minus 1 upon R minus 1. A is equal to 1, R is 3 is to n minus 1 upon 3 minus 1, that is greater than 1000. That means 3 is to n minus 1 is greater than 2000. That implies 3 is to n is greater than 2000. Solving this equation, we will get the value of n is equal to 7. If we raise the 3 to the power of 7, the value will be greater than 2001. 3 to the power 6 will be less than 2001. So our answer will be n is equal to 7. If the sum to infinity of a GP whose first term is A, then find the sum of first n terms in terms of A, S and n. It states that the sum to the infinite GP is equal to A upon 1 minus R is S, and the first term is A. We have to find the sum of n terms. Sum of n terms in terms of A, S and n. Sum to n terms, we know that the formula is A into 1 minus R is to n upon 1 minus R. Right? We don't know the value of R. The value of R can be obtained from this equation. R is equal to 1 minus A upon S. So the Sn will become A into 1 minus R, that is equal to 1 minus A by S raised to n upon 1 minus A by S. This will be the sum to the n terms in terms of A, S and n.